The Ramaswami power transformer. Recently, Mr. N. Ramaswami of India has produced a transformer design which uses alternating current mains as the input and at the present time has an output of more than 600 volts. It is his desire to share the information freely so that anyone may replicate his construction, and so, here are the details. The overall arrangement is comprised of several coils wound on a single magnetic core, which, in the case of the prototype, was constructed by inserting many iron rods of about 6 mm diameter, inside a standard plastic pipe of between about 60 mm to 100 mm in diameter. Several coils. The cores are made from a large bundle of uninsulated iron rods and seen from the end, the tube looks like this. There is a great difference between iron and steel because when subjected to a magnetic field, steel remains magnetized when the magnetic field is removed and iron does not. Normally, the iron pieces are insulated from each other in order to prevent eddy currents flowing between the separate pieces, but in this case, it is necessary to leave the iron rods uninsulated as performance has been shown to be improved with uninsulated rods. The way that the coils are wound and positioned is very important. The wire used has a cross-sectional area of 4 square millimeters and in the most simple arrangement, there are 8 coils. 2 of those coils are quadfilar, which means that they are wound using 4 separate wires side by side, with the end of the first wire connected to the start of the second wire, and the end of the second wire connected to the start of the third wire, and the end of the third wire connected to the start of the fourth wire. That style of coil, which was patented by Nikola Tesla, has very different characteristics to a simple helical coil, as the Tesla arrangement has a much greater voltage difference between adjacent turns in the coil. In circuit diagrams, the start of a coil is normally marked with a dot in order to make the connection method clear. A quadfilar coil can then be drawn like this. All of the coils in this construction are wound in the same direction and 2 of them are quadfilar wound. Initially, the first part of the secondary, output, winding is wound on opposite ends of the core, like this. Here, the first part of the first secondary winding is shown as S1, and it is a single layer of 85 to 90 turns. The first layer of the second secondary winding, with the same number of turns, is shown as S2. The N and S in the diagram indicate the magnetic poles caused when current flows through the windings. You need to realize, however, that these polarities swap over 100 times a second as the input is 50 Hz alternating current. Actually, the 2 windings shown plus 3 others not yet shown, form a single continuous secondary winding, even though when winding them before they are connected, they appear to be 5 separate coils. When those 2 initial layers have been completed, 2 separate quadfilar coils are wound on top of each of them, marked here as P1 and P2. How this winding is done is very important and has a major effect on the performance of the transformer. The P1 winding is started at the left-hand end and the turns are wound in a clockwise direction when viewed from the left. Generally, the winding is with a 4-core cable and the interconnection is completed by connecting the end of wire 1 to the start of wire 2, then end of wire 2 to the start of wire 3 and the end of wire 3 to the start of wire 4. The easy way to do this is when the winding is complete, to allow a length of the 4-core cable before cutting it. The extra length should be slightly longer than the width of the winding. The outer cover is then stripped back, which leaves a length of each core wire for making the connections. The wire end marked A will be connected to the live side of the mains and the wire end marked B will be connected to the neutral side of the mains. These connections are not random and need to be made exactly as specified here. This 4-core cable winding is the P1 section of the primary. The P2 part of this primary winding is created in the same style but is actually quite different. It is wound from the far end of the core, and it progresses inwards towards the center of the core. This time, the turns of the winding are made in a counterclockwise when viewed from the left-hand end. Winding the primary in this way is absolutely essential and care is needed when making the connections to the mains, or battery-powered inverter, providing the input power. Both of the A wires are connected to the mains live side and both of the B wires are connected to the mains neutral side. Make quite sure that these connections are made correctly, as this is a vital factor in the performance of the design. Next, those quadfilar windings have the final layer of the first two secondary windings wound on top of them. These are marked here as S3 and S4. Next, the center of the core is wound to a matching depth with the final part of the secondary winding S5. This is a single coil wound continuously with one single wire. The bottom layer is wound left to right and the next layer is wound on top of the first layer, winding from right to left, and the third layer is wound on top of the second layer, winding from left to right. The secondary gets connected up as shown below. The soft iron core is constructed from some bars which run the entire length of the construction, completely filling the central section, which runs through a 2.5-inch, 65 mm diameter plastic pipe, 12 inches, 305 mm long, and the two ends are surrounded by additional soft iron bars to fill 4-inch, 100 mm diameter plastic pipes at each end. The output from the secondary winding measures as approximately 630 volts, and so a step-down transformer with a ratio of about 3:1 is needed to lower the output to 220 volts at higher current, as 220 volts is more convenient, there being much existing equipment which uses that voltage. In 110 volts, American, parts of the world, the output transformer would be around 6:1 to give an output of about 110 volts AC. As the red quadfilar coil looks very much like an ordinary helical coil when shown on a circuit diagram, a little explanation would be no harm. A quadfilar coil has all of its turns in the same direction, just the same as any ordinary helical coil. Also, the current flow through a quadfilar coil is all in the same direction, just as in an ordinary helical coil. The big difference is in the physical positioning of the wires. In an ordinary helical coil, the voltage difference between adjacent turns is very small, but with a quadfilar coil, there is a major voltage difference between every pair of adjacent turns of the coil. That large voltage difference between adjacent turns makes a major difference in the electrical characteristics of the coil as a whole. The interconnection of the primary winding is very straightforward and is like this. This method of construction has the primary, 220V input, winding completely encased in the secondary winding in order to achieve the maximum induction from the primary winding. This is a rather unusual coil arrangement, which has a spectacular performance. The physical construction looks like this in cross-section. This shows how completely the red primary winding is enclosed by the blue secondary winding. The red input wire is connected across the 220 volts mains and draws 7 amps of current. The blue output wire has some 600 volts output voltage. A layer of very thin plastic, or alternatively, a layer of duct tape, is then used to enclose all of the windings. Then, one additional coil is wound to pick up power from the secondary coil. This extra winding has its number of turns adjusted so as to produce the 220 volts used by the input of the red primary coil. The final coil has fewer turns and looks something vaguely like this. Additional primaries and secondaries can be added to this arrangement. This arrangement results in only the primary winding being used in addition to the central secondary winding. This arrangement also uses all the opposite poles of the multi-module device, except for the first and last poles. The attractive force between all other electromagnets is completely used by the secondary. This arrangement results in both voltage and amperage increases in the secondary placed in the attraction zone, and any amount of voltage and amperage can be obtained. In our test arrangement we achieved about 630 volts and 20 amps, when providing an input of 220 volts and 7 amps, using a single module comprising just 2 primaries and 1 secondary. The system can be started initially from the mains through a press-to-make switch, as the circuit will be functioning and supplying an input in less than 1/10 of a second. If mains is not available at the location where the transformer is to be used, then the circuit can be started using a car battery and a 2000 watt rated DC inverter which has a true sine wave specification. There is probably no great reason why the starting inverter should not be one of the cheaper pseudo sine wave units.